In mathematics, an irreducible polynomial is, roughly speaking, a non-constant polynomial that cannot be factored into the product of two non-constant polynomials. The property of irreducibility depends on the field or ring to which the coefficients are considered to belong. For example, the polynomial x22 is irreducible if the coefficients 1 and -2 are considered as integers, but it factors as if the coefficients are considered as real numbers. One says, the polynomial x22 is irreducible over the integers but not over the reals. A polynomial that is not irreducible is sometimes said to be reducible. However, this term must be used with care, as it may refer to other notions of reduction. Irreducible polynomials appear naturally in polynomial factorization and algebraic field extensions. It is helpful to compare irreducible polynomials to prime numbers. Prime numbers are the irreducible integers. They exhibit many of the general properties of the concept of irreducibility that equally apply to irreducible polynomials, such as the essentially unique factorization into prime or irreducible factors. Definition: if f is a field, a non-constant polynomial is irreducible over f if its coefficients belong to f and it cannot be factored into the product of two non-constant polynomials with coefficients in f. A polynomial with integer coefficients, or, more generally, with coefficients in a unique factorization domain R, is sometimes said to be irreducible over R if it is an irreducible element of the polynomial ring. That is, it is not invertible, nor zero, and cannot be factored into the product of two non-invertible polynomials with coefficients in R. Another definition is frequently used, saying that a polynomial is irreducible over R if it is irreducible over the field of fractions of R. Both definitions generalize the definition given for the case of coefficients in a field, because, in this case, the non-constant polynomials are exactly the polynomials that are non-invertible and non-zero. Simple examples. The following 6 polynomials demonstrate some elementary properties of reducible and irreducible polynomials. Over the ring of integers, the first 3 polynomials are reducible, the last 2 are irreducible. Over the field of rational numbers, the first 2 and the 4th polynomials are reducible, but the other 3 polynomials are irreducible. Over the field of real numbers, the first 5 polynomials are reducible, but is still irreducible. Over the field of complex numbers, all 6 polynomials are reducible. Over the complex numbers, over the complex field, and, more generally, over an algebraically closed field, a univariate polynomial is irreducible if and only if its degree is 1. This fact is known as the fundamental theorem of algebra in the case of the complex numbers and, in general, as the condition of being algebraically closed. It follows that every non-constant univariate polynomial can be factored as where is the degree, the leading coefficient and the zeros of the polynomial. There are irreducible multivariate polynomials of every degree over the complex numbers. For example, the polynomial which defines a Fermat curve is irreducible for every positive n over the rails. Over the field of rails, the degree of an irreducible univariate polynomial is either 1 or 2. More precisely, the irreducible polynomials are the polynomials of degree 1 and the quadratic polynomials that have a negative discriminant. It follows that every non-constant univariate polynomial can be factored as a product of polynomials of degree at most 2. For example, factors over the real numbers is and it cannot be factored further, as both factors have a negative discriminant. Unique factorization property. Every polynomial over a field F may be factored in a product of a non-zero constant and a finite number of irreducible polynomials. This decomposition is unique up to the order of the factors and the multiplication of the factors by non-zero constants whose product is 1 over a unique factorization domain. The same theorem is true, but is more accurately formulated by using the notion of primitive polynomial. A primitive polynomial is a polynomial over a unique factorization domain, such that 1 is a greatest common divisor of its coefficients. Let f be a unique factorization domain. A non-constant irreducible polynomial over f is primitive. A primitive polynomial over f is irreducible over f if and only if it is irreducible over the field of fractions of f. Every polynomial over f may be decomposed into the product of a non-zero constant and a finite number of non-constant irreducible primitive polynomials. The non-zero constant may itself be decomposed into the product of a unit of f and a finite number of irreducible elements of f. Both factorizations are unique up to the order of the factors and the multiplication of the factors by a unit of f. This is this theorem which motivates that the definition of irreducible polynomial over a unique factorization domain often supposes that the polynomial is non-constant. All algorithms which are presently implemented for factoring polynomials over the integers and over the rational numbers use this result. Over the integers, the irreducibility of a polynomial over the integers is related to that over the field of elements. In particular, if a univariate polynomial f over is irreducible over for some prime that does not divide the leading coefficient of f, then f is irreducible over. Eisenstein's criterion is a variant of this property where irreducibility over is also involved. The converse, however, is not true. There are polynomials of arbitrary large degree that are irreducible over the integers and reducible over every finite field. A simple example of such a polynomial is the relationship between irreducibility over the integers and irreducibility modulo p is deeper than the previous result. To date, all implemented algorithms for factorization and irreducibility over the integers and over the rational numbers use the factorization over finite fields as a subroutine. Algorithms. The unique factorization property of polynomials does not mean that the factorization of a given polynomial may always be computed. Even the irreducibility of a polynomial may not always be proved by a computation. There are fields over which no algorithm can exist for deciding the irreducibility of arbitrary polynomials. Algorithms for factoring polynomials and deciding irreducibility are known and implemented in computer algebra systems for polynomials over the integers, the rational numbers, finite fields and finitely generated field extension of these fields. All these algorithms use the algorithms for factorization of polynomials over finite fields. Field extension. The notions of irreducible polynomial and of algebraic field extension are strongly related, in the following way. Let X be an element of an extension L of a field K. This element is said to be algebraic if it is a root of a polynomial with coefficients in K. Among the polynomials of which X is a root, there is exactly one which is monic and of minimal degree, called the minimal polynomial of X. The minimal polynomial of an algebraic element X of L is irreducible, and is the unique monic irreducible polynomial of which X is a root. The minimal polynomial of X divides every polynomial which has X as a root. Conversely, if is a univariate polynomial over a field K, let be the quotient ring of the polynomial ring by the ideal generated by P. Then L is a field if and only if P is irreducible over K. In this case, if X is the image of X in L, the minimal polynomial of X is the quotient of P by its leading coefficient. An example of the above is the standard definition of the complex numbers as if a polynomial P has an irreducible factor Q over K, which has a degree greater than 1. One may apply to Q the preceding construction of an algebraic extension. For getting an extension in which P has at least one more root than in K, iterating this construction, one gets eventually a field over which P factors into linear factors. This field, unique up to a field isomorphism, is called the splitting field of P over an integral domain. If R is an integral domain, an element f of R which is neither 0 nor a unit is called irreducible if there are no non-units g and h with f equals gh. One can show that every prime element is irreducible. The converse is not true in general but holds in unique factorization domains. The polynomial ring f x over a field f is again a unique factorization domain. Inductively, this means that the polynomial ring in n indeterminates is a unique factorization domain if the same is true for R.